Good morning, everyone. I'm going to introduce a scientific view on the winter gardens of Lacaton-Vassal. So, Lacaton-Vassal are architects that have been working with greenhouses for over 30 years. They are very technical structures, perfected to allow as much sunlight as possible, protecting what is below from the weather. They have domesticated this technology, use it in housing and any kinds of buildings. So rather than using insulation, airtightness, and technology, they prefer to use space, buffer climatic spaces to naturally progress from the exterior to the interior, using the sun as a natural warmer. 7 years ago, we embarked in a research project to actually understand the environmental performance of these spaces. How much sun do they have? How much light? How is temperature? So we have conducted all this research for the past 7 years with them, and published this book last year that is called It's Nice Today, on climate, comfort, and pleasure. So as spaces that are extremely exposed to daylight and to the sun, with daylight and sun comes exposure to outdoors, comes an increase of temperature when the sun is there and cold when it is not. So we really try to understand how these spaces behave in time, how do they receive the sun, how they actually work in real life. So the first thing is that we went to many of their buildings, we interviewed the people living there, we took measurements, and the first thing that comes out is that people are really happy with greenhouses in their homes. And this is one of the nicest quotes. I feel a sense of calm in the greenhouse, a sense of well-being. I'm not being suffocated. It's a privilege to be here, to have this space, not to have ceilings and walls that are oppressive. When we live, we miss the light. The greenhouse is a continuation of the house. It's not quite the garden, but a pre-opening to the garden. So we studied how they applied these greenhouses into different housing projects. So they have really domesticated all the technology that comes with greenhouses and applied it to buildings across time. So these are spaces that cover the facade entirely, that follow the main living space, and are always facing south. They are applied to units that can always cross-ventilate, so it's very important to be able to allow the sun, but also to release the heat. So from the outside, buildings look the same, as the focus is on the experience of the winter garden. And they are also extremely technical, so when we see them from the outside, it would seem that it's always the same, because the final element is a solar curtain that has to be reflected aluminum to be able to reflect the sun out when it's not needed. And it's always applied, they apply their greenhouses on climates that allow it, where heating is the main concern, but there is enough sun to capture on it. So it's a space that, in principle, has just better conditions than outdoors. It's not an indoors. It's just an intermediate space. It's a space where we can be in there during the mid-season, during winter, as a better outdoors. It's not an indoors. And this is actually a key factor to understand that we are not supposed to put a heating device in a winter garden. And actually, when we did our interviews, no one does so. So, as I was mentioning, it's very technical, and they always repeat the same structure in all their projects. So there is always an outer layer that is a polycarbonate structure that slides very easily to be able to open and close. And even in buildings that have been built for over 15 years, it still works perfectly fine, and there is no issue in opening. There is a solar curtain that reflects the sun as it's finished with aluminum, and the percentage of opening is very precise according to the project and what the space needs. Always, the winter garden is made of concrete, which concrete naturally stabilizes temperatures. Then we have a double glazing, and then in the end, a thermal curtain to close when there is no sun and to create more insulation. So in winter, when everything is closed, when all the glazings and curtains are closed, then the space becomes a buffer, and it's a better insulator to the interior space. And in summer, everything is open, the air passes, and it acts like a terrace. So the environmental benefits that these spaces offer are endless, but people are very skeptical about these, because if they are not properly designed, then they can cause overheating very fast. Then they can be a problem to the main space. They can be used as storage spaces. So it can be very easily a problem. But if they are properly designed, then the environmental benefits that these spaces can bring are just endless. So they are a shaded outdoor space in summer, protected semi-outdoors in winter. And in the mid-season, they become just a larger indoor space because the intermediate glazing can be left open and the main space is enlarged. They act as a buffer effect, so they are a better exterior to the main space. It reduces heat loss and infiltration of the main building. It actually minimizes the heated envelope, so during winter we are in a smaller space, but during the mid-season and summer, when the weather allows, we can occupy more space. It's a natural preheater of fresh air. So for winter, the air first comes to the winter garden and then inside. So it's naturally preheated, not mechanically, which is actually also very good to reduce heating loads. So in winter, we can open better our windows because we are opening to a better exterior. It allows generous daylight and views. It allows seasonal adaptability for occupants. And because we have these elements, the balcony, the solar curtains, it has plenty of solar control. So we studied the application on four case studies in Cité Manifeste, in Mulhouse, in Orgeres, in Paris, in Grand Parc, in Bordeaux, which is a building that also won the Mies van der Rohe Award, I think, in 2020 or something like that, and in the Opel Tower in Genève. So this, as I was mentioning, winter gardens are very systematized, always facing south, always following the main space, always a possibility to enlarge this main space, and obviously because they are so exposed, because they are so exposed to the weather, plenty of daylight, plenty of sun in. So we studied these spaces with a scientific view, with a scientific methodology that doesn't involve narrowing down the result to one number, to one point in time definition of the space. These are spaces that change with the weather, that change with the seasons, that change with the time of the day. So during the day, curtains are open, at night they are closed, the resulting temperature is not the same, nothing is the same, the spaces evolve, and we have to have a way of accounting all of this. So first, we studied carefully how does the sun heat, because the depth of the winter garden will vary the amount of sun, and the depth of the balcony will always have a 50, 60 centimeter balcony at the end of the winter garden. So all these depths and how it is oriented will change the amount of sun both the winter garden and the interior space receive in a day. So because during summer the sun is higher, the sun does not reach indoors, so the indoors is always protected from the sun. Windows are always very open, so there is no overheating. During winter, because the solar angles are lower, the living room and winter garden are in full sun, benefiting from passive solar heating. Then we not only accounted for sun hours a day, but also how much heat does the winter garden add to the interior space. And actually, when we count for solar gains only when everything is closed. When everything is open, there is no need to count how much heat. And generally, they tend to open 3/5 of their doors, so it's quite operable, so that the heat doesn't accumulate that much in summer. So in winter, actually, we did the calculation, and it's almost like having a radiator. Then how does the air flow? How does the air passes through in these units when everything is open? And we take average conditions, so average wind speed what happens if everything is open. So the unit benefits from cross-ventilation in summer when under average conditions. Everything can be open, and they always maximize this opening space so that everything can cross-ventilate. Then, of course, how much daylight do we have inside? And we use daylight autonomy, which calculates the percentage of time that a certain point in space receives 300 lux or more. And this is a fear that most of the people have. Oh, behind the winter garden, because it's so deep, it can be dark. But actually, the winter garden allows so much light in that actually spaces are very bright. All the space is always in autonomy, even in the deeper parts of the house. And then we did some fieldwork. We also measured temperature. What's the resultant temperature of this space across the year? So we left temperature data loggers in different points in the housing, and we of course did this process in the 4 case studies. I'm just taking the one that we think is most representative. So we left 1 data logger outside, 1 in the winter garden, 1 in the main living space, and 1 in the bedroom. So what was mostly important for us is to understand how was the temperature of the winter garden in winter. So we left it during a week, 10 days in December. Here you can see the lower curve is the outdoor temperature, the second curve is the winter garden, and then indoor temperature. And just as a comment, this space has central heating, so temperatures in winter are far too high. This was a learning that we extracted from the research, but what was very important for us is to understand how much higher is the temperature in the winter garden compared to outdoors. So on sunny days, what we found out is that the winter gardens can be up to 8 degrees above outdoors, and during cloudy days, because the concrete retains the heat, it's more or less 3 degrees higher than outdoors. So this is a much better exterior space than just outdoors. The second step for us was to actually calibrate a thermal model. So we built up a thermal model and we calibrated it to the real measurements. So in here, you can see, again, all the plain lines that were measured temperature inside the spaces. All the dotted lines is a thermal model that we calibrated to these real measurements. So what happens in the process of calibration is that we can actually understand exactly how much air change is passing via the winter garden. Do we have the real properties in the concrete of how much thermal inertia is it holding, or are objects covering that inertia? Do we have the real amount of sun heat that is passing via the glazing? So when all these properties are properly calibrated, and then we can actually mimic quite fairly the temperature that happened in the winter garden. And what we have with this is a model that can mimic reality quite closely. So this was above 90% close to reality. So then when we introduce a different weather scenario, when we can see what happens in summer or in the mid-season, we're fairly sure that the simulation actually will behave as reality. So this is the R square, so the precision that this model has is more or less 93% compared to reality. So when we do a prediction, we're fairly certain that we're predicting relatively close to reality. So then we saw what happens across the year, what happens in different scenarios, what happens if there would be another winter garden on the other side, what happens with this space in different conditions. So I'm going to go one by one, what happens in winter. So what we calibrated is air temperature, but then we can also see operative temperature, which is closer to the felt temperature, as it accounts for air and the surface temperatures. So this was the simulation for winter, but because we saw their measurements, I'm not going to go in depth on them. What is interesting to understand is that it's just a better outdoors. During winter, we're not supposed to use this space as an indoors. It's just a buffer. It's just a precisely winter garden. And we also calculated how would be interior temperatures naturally. So on the living room, in a December week, we would have naturally in between 15 to 19 degrees, which is actually livable. We wouldn't need to heat up. If we were in the 70s, these were the natural temperatures that spaces had, and these were the temperatures that any building would reach up until the 70s. So we would actually not need heating. We wouldn't have to even speak about energy. We don't need it. Then what happens in summer? In summer, because we open so much these doors, because we have solar curtains, because the concrete actually shades the interior, then temperatures are very close to outdoors. And not only that, at peak times, the winter garden can have lower temperatures than outdoors because the concrete retains the cold from the morning. So it's even better for summer. So if doors are wide open, then a winter garden can be nicer than outdoors, even at peak times in summer. And during the mid-season, what happens is that when the weather allows it, then the temperatures of the winter garden reach comfortable temperatures as an indoors. So we just open intermediate spaces, we enlarge the living space, and it's just an extension. It acts as a simple extension. So during day and night, in the mid-season, temperatures inside the winter garden are 4 to 5 degrees above outdoors if there is no sun, and if there is sun, it can be much, much higher up until 7 or 8 or even more degrees above outdoors. So it's a space that is extremely versatile, that allows us to live with the sun, that allows us to have daylight, that allows us to enlarge the living space, to have a terrace. In the summer, they are very useful and pleasant living spaces to have. We even saw what happens in extreme days. So if you think about it, the coldest days are usually sunny. So because the sun increases more the temperatures inside the winter garden, they are very useful for extreme cases. So the north, I also added the comparison case here. So the south winter garden can have maybe 9 degrees during the day when outdoors is below 0, which is actually quite great. Even in extreme days, we can be outdoors. And this is a very nice sensation to have. And during an extreme summer day, we do have 2 to 3 degrees below outdoor temperature. So it's really a space that is great to live with. And we also did some comparison cases. What happens if we added a north winter garden in the same structure? It will actually be better and increase general indoor temperatures. What would happen if we change the winter garden for a triple glazing? Then no, the triple glazing is not more useful than the winter garden. So we really made quite a lot of comparison cases to see if there was a better scenario. And really, a winter garden that is technically done was the best scenario that we found out of everything that we went on. And this is a graph that can be very technical. It's just comparing outdoor temperature to the winter garden temperature. So if the dots here that represent temperature at different moments of the year would be in the diagonal, it would mean that outdoor temperature is the same as the winter garden. And here, what we can see is that the lower the temperatures, the higher the difference between the winter garden and outdoors, meaning that it becomes more effective. The higher the outdoor temperature, then the closer the winter garden temperature comes to outdoors, and at peak times, it can even be below. So it really works like that across the year. And the energy demand is finally lower, so we propose to see temperature not to start with the energy demand, because in the end what we want to create is spaces that have good temperature, good light, good ventilation, and that's just enough to be fine. Perhaps we don't need energy. Today we're asking buildings to be all the time at 20 degrees. That's just far too much. So we think that up to a point, the buildings can deliver a lot and can deliver naturally. And sometimes, perhaps, we just have to lower our expectations on energy, on what energy has to compensate. But even so, we always calculated the energy demand that these buildings need, and it's always low. It's always below 15 kilowatt hours per square meter, which is what today is asked for most buildings. And what is more interesting is that the temperature and the heat supplied to these buildings is mainly based on the sun. So the solar gains are the largest heat contribution across all the projects that we studied. So it's a lot better to count on solar gains rather than to count on internal gains or just heating to provide heat to an interior space. So with the sun comes heat, comes light, comes just a pleasant living space if we can compare it, if you can actually design it properly. So this here was the added winter garden in the north. So if we even added a winter garden towards the north, the heating demand would be 10 instead of 15. So it would even be better to have a winter garden towards the north, but as you may expect, architectural projects have constraints that are not just whatever we can do, so sometimes we can't. So we did this work in all the projects, so even if I just showed you one, the results are very similar in the different climates, in the different typologies that we studied. So this is just a scientific view on how winter gardens behave to actually temper indoor conditions. I generally have a last slide that is, don't fight climate, use it.